Hello everyone, I'm Charlotte from MDPI and I will be your host for today. Welcome to the first live session of the first International Conference on Micro Machines and Applications, ICMA 2021. This e-conference is hosted online from the 15th to the 30th of April 2021 and is organised by MDPI and the journal Micro Machines. During this time, the conference presentations will be available for discussion on the conference website. The accepted abstracts will also be available in the journal Engineering Proceedings. I would like to thank the conference chair, Professor Ion Stiharu, the conference committee and the session chairs for making this e-conference possible, along with the speakers and of course our attendees. Today's live session is chaired by Professor Ion Stiharu from the Department of Mechanical and Industrial Engineering at Concordia University in Montreal, Canada. Thank you for chairing this session, Professor. There will be 4 presentations today, and each presentation will be followed by a short question time. That's it from me. Now it's time that I hand over the microphone to Professor Stiharu to officially open the conference. Thank you and enjoy, everyone.
Good morning, everyone. Good afternoon for some. Depends on where you are in the world. I think that was the biggest challenge we have with this conference. The fact that we have to see each other at different times, and what I am calling morning might be late night for others. So I really want to thank you very much for making this possible. The idea of this conference came from MDPI, of course, and I suggested to have this conference on the subject on applications of micro machines, as I believe times are such that they require the contribution of science people to very practical and concrete contributions to the needs that community needs as a fact. I have a word of welcome. I don't want to repeat that. I just want to point out a few details. The fact that we need everybody that it's willing to do science to step in and do science. Science is the older, I don't know, technical revolution, the technological revolution of 250 years ago. Now we face this science revolution, which sure it's combined, it's tangled somehow with the information revolution, information technology, and they will contribute definitely to new findings that are absolutely necessary to the humankind. And I want to bring tribute here to the research community, not ours, but another research community. They were able to produce a vaccine in such a unbelievable and never thought possible time. So, and this is basically the power of science under the conditions. So I want to thank you very much again for attending. I believe there are few attendants in this session of today, the first live session that we have. With a further ado, I would give the microphone to the first presentation in this session. In this kind, it's Dr. Junsuk. He will have a presentation that will follow right now. So I pass you the mic.
Okay, so thank you very much, Professor Stiharu, for introduction and invitation from MDPI. So I'm very happy to present our recent work about this micro nano fabrication. So especially, you can see the main concept today is achieving the chirality, how to make a micro nanoscale chiral structure for plasmonic metamaterial application. So I will show 3 to 4 different fabrication strategy, and also each fabrication related to the different side of the structure. So you will see the from terahertz to IL and visible and full shorter visible frequency. So okay, so our group post-tech from Korea, I'm working on like a super resolution microscopy and cavity and recent meta surface. But today, as I mentioned, I focus the 3D nanofabrication and some of micro, and to realize this chiral metamaterial structure. So if you compare, so I'm very happy to see the last speaker today is Professor Marc Madou. So I learned, from his book, so microfabrication. So right now the micro technology or some electronics, we see all the mature technology. So main reason is, all the microstructure now is like a factory scale. Manufacturing is doable, and three-dimensional any arbitrary structure is very easy to make right now. But the problem is in nanoscience, still we are relying on this prototyping technique like e-beam lithography, ion milling, and so on. They are very low throughput and low frequency, low efficiency, and not easy to making three-dimensional, like some arbitrary structure yet. So actually, this is all the homework in the community facing, like how to achieving scalable fabrication, like manufacturing, and also this how to making three-dimensional nanostructure. So I show today two approach from the lithography top down, and two other one is from bottom up, so chemical synthesis, and the last one is a little bit hybrid fabrication technique, so published 2 weeks ago. So actually my interest about chirality started from this slide, how to achieving this negative refractive index, this Veselago proposed 50 years ago. If you see the revisit this Snell's law, n squared is epsilon mu. So we know to making this refractive index a negative number, is supposed to be epsilon and mu is both negative number at the same time. So it had been not realized, from 1960 until 2001. So this is from Duke achieving the double negative epsilon and negative mu by this array of metal and the double split ring resonator. So making this one together, they have the both double resonant and minus in 10 gigahertz. So this is the first experimental demonstration of negative refractive index in microwave regime. So after this work, many pioneering work to realize this negative refractive index. But the problem is finding such a design. So double negative epsilon and mu is very hard to find. So we proposed like 15 years ago, this achieving artificial chirality in such a structure in 3 dimension, and it's a shift. It helped achieving negative refractive index a little much easier. So without double negative number, we can achieve negative refractive index. So how to do that? This chirality, we can see in the nature, like a DNA and such shell, or some of chemical, like a lemon and orange, they have a same chemical, but left-handed, right-handed, so they show different taste, right? And we first time like 2009, we achieved such three-dimensional chiral structure using microfabrication, and this is all made by gold, and this is like can be considered as a LC three-dimensional LC circuit. And in this case, we can make it the making coupling between this magnetic and electrical response. In the certain case, like Snell's law, can be a little bit modified. So now n squared become epsilon mu plus something. So this something is coming from chirality. So if this something become large enough and negative number, and then we can achieve a negative refractive index very easily. So this is based on this microfabrication, so we achieve the switching performance, like the normal case, like a positive index, and then switches on by external stimuli by shining the light and become like change it to the negative refractive index. So how to do that? This is a two different chiral structure, left-handed, right-handed, and combine this together, each have their own chiral circular dichroism response. So this is plus and minus. So combining these two, just making cancel, so nothing. And we introduced a little of the anisotropy. So this part is replaced by silicon. So the other is all gold. And in this case, this silicon is like dielectric. So the LC circuit's length become shorter. So their resonant frequency become moved to the higher. And here another silicon, but they don't do any effect here. So combining this molecule of A and B, we can make like a positive circular dichroism resonance. But if we shine, this silicon work as a conductor. So the length of this LC circuit become to the come back to the original length. So the resonance become shifted again. And in this case, horizontal silicon hinder the response of this CD here. So combining these two, making negative circular dichroism response. So plus minus, we can change the this chiral response. So as I mentioned, this is microfabrication. So unit cell size is about 50 micrometer. So we use like, this is a mask, the top view design. So this is a hole. So we do first lithography on silicon on sapphire wafer. So this is the first lithography and etching of silicon. So this is a bottom pad of silicon. And then we coated with the aluminum for the next step, like the fourth step, we do electroplating. So we need the electrode at the bottom. And then this is the second lithography. So you can see the alignment, as usual, micro mask aligner can do alignment very good. So this is a gold pad lithography, and then gold deposition and lift off. Third one is we coated with spin-on glass. So spin-on glass making the electrode making safer during the electroplating. So anyway, so you can see the here anchor. Anchor is the starting point of the long this pillar. So this is the fourth lithography in SC8. We make this long via hole, and electroplating is being done here. So coming up, and the fifth lithography making the top structure of a V-shaped antenna. And then we do a little of a micro welding here to making the connection between this pillar and this final antenna. And then lift off, and it's done. So this is a micro scale working in terahertz frequency, negative refractive index metamaterial. So it published almost 10 years ago. So experimentally, you can, very easy to do that. So we confirm negative refractive index exists. But my next question is come from from previous slide is wanted to making this one in the shorter frequency visible, at least IR, and then we can make a more application like invisibility clock, invisible frequency, and so on. But the problem is, you can see here existing all the visible frequency metamaterial is like very thin, because made by e-beam lithography. So now we call this on meta surface. And this is what I made, using microfab. So this is a micro scale working in terahertz. So using FIB, like e-beam lithography, direct laser writing, and this chemistry, they all have a pros and cons. FIB is a very sophisticated structure, but some very few people can do that. Direct laser writing, 3D printing. So this is very good, but we need electroplating, and some of limited in terms of the design. So our approach is using e-beam lithography, just doing overlay, and then I realized this is also not easy, so we cannot achieve a visible. So we use the chemistry, so making much smaller chiral structure. So I show two examples. One is using e-beam lithography overlay for near IR chiral metamaterial, and then bottom-up synthesis for visible chiral metamaterial. So this is what happened in microfab. So this is a second layer mask, and this is first substrate. The pattern is done. So alignment is not good. So we do making rotation and translation, making alignment okay. So we can see alignment mark. So good exposure. So go on. But the problem is e-beam lithography. So we are not allowed to see alignment is good or not, because scanning electron microscopy also used as a microscopy, also at the same time as an exposure tool. So we are not allowed to see them. So we cannot directly align them. So indirectly, the virtual align mark. So we do alignment. So at this moment, alignment is assumed good, but we are not allowed to see. But anyway, with the exposure. So after this process and do deposition, lift off, and we see, check by SEM. So it's not easy job, but anyway, so we have a pretty good this alignment skill. We did this coordinate compensation, the stage and some of experience. So about 20 nanometer overlay misalignment with about 70% of yielding success ratio. So we tried to making the previous micro chiral metamaterial about 150 times smaller. So this is the first lithography by e-beam, and then gold deposition lift off. And then second one, PMMA, and again making hole here, deposition lift off. And then third layer, a little tricky, because if we exposure here, and then normally the beneath of this suspended, the bridge also exposed. However, so we do like, grayscale lithography, only expose the certain depths of the photoresist on only few tens of nanometer on top. So, and then we do deposition left off. So that makes this suspended nanoscale, this 3D chiral structure. So it works okay. But the problem is that this is the smallest size we can make by our e-beam lithography. But the problem is still only 1.5 micrometer working frequency. So we couldn't make much smaller than this one. So top-down approach, so we had some limitations. So I was a little disappointed, but realized many people, they have many different skills to achieve the visible frequency chiral metamaterial. So this is by e-beam lithography, but different design. And this is using purely deposition technique, glancing angle deposition from Max Planck. They rotate the stage and they can making this zigzag structure by only deposition. And this is a direct laser writing from Karlsruhe group. And this is beautiful technique also. And more recently, this chemistry guy using DNA origami, and then they making this golden nanoparticle is about chiral in template. So this is beautiful. So later I compare with this slide of this center in Nature 2012. So it showed the highest chiral property so far, but our chiral metamaterial actually 10 times larger optical response than this one. So I will show how we do that. This is a typical golden nanoparticle chemistry. So starting from golden nanoparticle seed, we change the this temperature, pH, and concentration, and then reduction agent, and we can make such a structure, so like a cubic, tetrahedron, octahedral structure. But you can see they all have this symmetry, so they are not chiral, so they are achiral and symmetrical structure. And then some people demonstrated this one, like calling high Miller index nanocrystal. What it is, they start from certain the low Miller index nanocrystal, and then they do second step, hierarchical growth of this chemistry. So in following some certain line, so they having evolving some of the second hierarchical structure. So you can see their shape is become little complex than this one, but still they have all achiral, they have all symmetry. So chirality still does not made. But anyway, we can do that this one very easily. At the same time, we investigated some of the literature how this nature having chirality and other people how to achieve this chirality. So this is the well-known this some beetle. They have a different color depending on left-handed light, right-handed light, because their skin, they have some chiral structure in their this skin. So they have a different absorption between left-handed and right-handed light. So the color is different. So that exists in the nature, that chirality. And this is more direct evidence. We having some clue. So this is a shell. This is a biology paper. They show the shell growth mechanism. So we know shell has a helix in the eventually, but when they born and grown up, they don't have a helical structure at the beginning. So their growing speed of this shell is all same speed. So no chirality here, but certain time, this helix started to be made. And this biologists found the certain protein level dramatically increased when the evolving it is happen. So this chirality is related to this protein somehow, our hypothesis. And then the other clue, the material of this shell is called calcite. Calcite is known this high Miller index plane. So what it means, we have some clue. This high Miller index plane and protein did something for this chirality evolution in nature. So we just try, copying the nature. So this is a golden nanoparticle growth in the normal, this inorganic case, and we added this organic amino acid. They have a left-handed, right-handed, and during this golden nanoparticle synthesis, we added this guy, and magically the left-handed chiral nanoparticle, right-handed chiral nanoparticle exactly mirror, and it's happened. So inorganic material is of organic chirality is transferred to the inorganic growth. So after we found this scheme, so after that we now is very easy. So we try a lot of different concentration, temperature, and growing condition, different peptide, different protein, and so on. So it was really interesting. But why people didn't know before? So the problem is here. So this is a cysteine, one type of amino acid, and amino acid is exposed to this such a golden nanoparticle. So they don't do any reaction. Although the thiol is like a gold, they don't have any interaction between two. But if we don't use this nanoparticle, so a little more complex structure, this is called the hexoctahedron, having high Miller index plane of 3 to 1. And now these guys start to interact with this golden nanoparticle. So this cysteine having some of limited binding to the high Miller index plane, so not low Miller index plane. This is a 111, 100, 101, but this is like a 3 to 1 high Miller index plane. So this is a basic 3 to 1 R, 3 to 1 L, and left-handed amino acid bound here, right-handed amino acid bound here. So they interactively change the growing direction. It's like curling the counterclockwise here. So without this amino acid, so they just growing this 111 direction symmetrically. But this case, gradually changing the direction and growing like this way. So eventually we see such a helical shape in this golden nanoparticle. So this is the macroscopic scanning electron microscopy image. So you can see chiral, not identical, but if we measure this ensemble, it's quite averaged out. So this is a case of if we cut this plane like 110, and this is like a growing direction of this chiral tail, and 100 is like this one. And if you're making three-dimensional image, so like a 2-hour process, the helical edge become growing like this one. And this is a self-stopping process after all the amino acid is gone. And this is optical measurement. It's left-handed chiral nanoparticle, right-handed chiral nanoparticle. So they have exactly mirrored CD response in visible frequency. So this is not active, so we cannot change this peak in the real time, but we have many different case of the growing condition. So we can tune from 400 to 700, so many different particles. So, okay, I skip this one. And once the cysteine case works, so now we use another, the peptide glutathione. So this has different evolving scheme, but eventually the purpose of this using glutathione is same. So shape is a little different, but anyway, they have the same geometry. So this one, shape is different, but they have all the four-fold, three-fold, two-fold rotation axis, so they don't have a mirror plane. So they have a chiral shape. So we conclude they are 4-3-2 symmetry group. So the name now we call this 4-3-2, helicoid 1, 2, 3, 4, 5, 6, and so on. So anyway, so at this moment, helicoid 1, 2, so we start from cubic seed. But now we try to starting from different base octahedral seed. In this case, the helix become much larger. So this is the highest G factor, highest chiral response we having. So we use this one for further optical characterization. So this is a helicoid 3 with the highest this chiral, some geometry and optical property. So we measure G factor. G factor is a circular dichroism divided by absorption. So this was the previous world record case, 10 to the minus 2 at the visible, but we have a 10 to the minus 1, so 10 times larger. So what we can do, 10 times larger G factor is 10 times larger absorption behavior in left-handed and right-handed. So what we can do, one example is like a changing polarization. So this is a nanoparticle, and this linearly polarized light is come in, and this changing of azimuth angle and ellipticity is changed by this optical rotation performance. And even this is more interesting, the plasmonic color, the nanoparticle, normal nanoparticle. So linear polarized light comes in, nothing happened, just passing through. And here vertical polarizers, nothing coming out. So no color happened. But chiral particle case, they have optical rotation. So this horizontal light rotated and some portion is coming out. So we see some color. So using this concept, so we making some more variety of color than achiral sample. So achiral, 0 degree means like this vertical horizontal case, no color, and counterclockwise rotation of second polarizer, same color because they are symmetrical. But in chiral particle case, different color because they don't have a symmetry. So using this one, some real-time plasmonic color change, although the contrast is not good because the loss of this plasmonic material. But anyway, we can make a pretty, variety of a color in using different nanoparticle. The color cover this sRGB color gamut in display, and color mixing is like a dye, A plus B making the color of C. So anyway, so we are trying to use this one for more, some interesting application like a color filter and so on. And original our motivation, whether they have this the refractive index in negative number in visible. So the measurement is still ongoing, and more different type of helicoid 4, 5, 6, and so on. And not just for gold. So we can do silver and aluminum, platinum, cobalt, and all this inorganic material if they have the high Miller index plane, and then proper this binding mechanism with this chiral organic material. So that was our recent work. So now what we are doing is using this deep learning. So because current problem is we don't know until the final structure made and then measure. So now what we are doing, we ask inverse designs. We fix the wavelengths or some optical property. So green color, so we need this circular dichroism of something, and no angle dependency, and what would be the fabrication synthesis condition, and then we use that one, and then we just finding the proper chiral particle very easily. So it's called like a design for manufacturing scheme using deep learning. So this fabrication would be much easier in near future. And this is the last two slides I'm gonna share. So 2 weeks ago, we succeeded to making 3-dimensional nanoprinting by a charged aerogel. So this is a gold nanoparticle, charged nanoparticle. And then we using this charged Faraday line mask, and then this 3-dimensional arbitrary structure with the sub 100 nanometer resolution. So gold nanoparticle is basically, it is, stacking here. So this is such a chiral structure we can make with very high yield and large scale, the large area size. So this is some example. We can make a chiral structure with such a nanoprinting technique based on charged aerogel nanoparticle. So such as 3-dimensional split ring resonator, and so some, some this T-shaped structure, and more like this, anchor type. So still, we're trying to make it more structure based on this scheme, but usefully would be very good in 3-dimensional nanofabrication. So this is my summary slide. So based on this 3D chiral metamaterial, so I show 4 different fabrication: photolithography, electron beam lithography, and chemical synthesis, and our homemade technique of the aerogel printing. And then they have a different like pros and cons. So no exact answer. So it depends on what wavelength you want to do and what would be your application using this guy. So new and hybrid fabrication technique is being developed, not just by our group and the many other groups in the world. So hopefully, this nanofabrication technique become better in the future. So thank you very much. So this is our reference and acknowledgement. So thank you very much of your attendance, and thank you, guys. Thank you. Bye-bye.
Thank you, Dr. Rowe. Very nice and comprehensive presentation of a really amazing work. So you convinced me that what I see is not what it is, right? In other words. So I checked during your presentation if it's any question. I can't really see any. Very nice presenting, thank you. So I don't see any question. If it's any, I'll wait for 1 minute. Meanwhile, sure. I wish to invite Dr. Caltabiano to prepare.
Okay, perfect. So thank you. I'm Daniele Caltabiano from STMicroelectronics. I will present this work on piezoelectric ultrasonic micromotor. Okay, so the idea behind this work is to miniaturize a traveling wave ultrasonic motor, but also make it possible to be fabricated in planar technology, so for microfabrication in silicon foundries. Here on the left, you can see in this animation the map of the vertical displacement of a vibrating disk. So the disk is fixed, so nothing is rotating, but you can see from the animation that this vertical displacement is somehow rotating clockwise. So we will see this a little bit better in detail afterwards. So the motor is composed of 2 parts. The stator is will be mostly investigated during this presentation because it contains most of the complexity of the system, and the rotor. The size of the system is about 2 millimeters in diameter, and let's see how the stator is composed. So from one side, on one side, we have the piezoelectric electrodes. You can see they are 12. And we have on the center some contact pads. So the central for ground, for example, and for contact pads for the electrodes. On the other part, we have a comb finger structure, which is with 200 micron thickness. Let's see how the microfabrication process works. So we have both sides of the silicon wafer processed in this case. So in the front, we start from the front, we have the PZT stack on top. You can see the two electrodes, so the ground and each of the 12 electrodes here on the top, and some metal for connection of the electrodes. After the PZT stack, we have some dry deep etching in order to start the singulation of the system in a circular manner. So here you can see in the top view the 12 electrodes, but also some connection, metal connection to the central pins. At this point, we flip the wafer from the back. We start with a deep etching in order to fabricate the comb finger structure. And at this point, we need to solder the first wafer on top of a second wafer that can be part of the, for example, of the final assembly, or can be a temporary support. Why this temporary support? Because at this point we do a further etching or lapping of the surface of the substrate in order to reduce the thickness of the comb finger at the desired height, but most of all in order to separate all the stator in the circular shape. So at this point, each stator is singulated, and so we need a temporary support or the final, let's say, substrate for the assembly. As regarding the assembly, we didn't go so further in the study, but we assumed two possible assembly structures. So the first is let's say a more traditional assembly with some spring holding the stator on top of the rotor. Here you can see the rotor and the connection to the substrate. Here are the electrical connection that are brought to the external part of the package, and some spring that are holding down the rotor on top of the stator. In this other case, we have a stopper which is mounted directly on top of the stator in order to hold down the rotor on top of the stator. Let's see now how the simulation has been carried out. We used the COMSOL multiphysics finite element software, and here you can see the constraint. So the rotor has been, this is a section of the system, the rotor, the stator is fixed on the bottom, so this circular part of the stator is fixed, while the rotor is free to rotate along a vertical axis and placed at 5 micron distance from the stator. We first analyze the stator by itself, so the resonant mode of the stator, and we selected the third mode, vibrating mode, which was around 50 kilohertz. Why the third? Because in this case, As you saw also in the first animation, we have 3 contact points between the stator and the rotor. So we have a solid connection between the two. Since the mode is 3, we divided the 12 electrodes into 4 groups of 3 electrodes. In this case, electrode number 1, 5, and 9 are actuated, they are controlled together, and so for 2, 6, and 10, and so on. For each one of this channel from 1 to 4, we have a sinusoidal voltage. We applied a sinusoidal voltage monopolar from 0 to minus 30 volt in order to keep the polling of the piezoelectric material. In this animation, you see again the vertical displacement of each finger, but you can also see the lateral movement. If we plot this lateral movement, this movement along this plane on a graph, we see an elliptical trajectory that is forcing the rotor to move towards right in this graph, while the traveling wave we can see is moving on the other direction. This is a temporal simulation, only 600 microseconds. You can see that the linear simulation of the vertical displacement versus time is diverging. If we enable the nonlinear part of the finite element simulation, we have reduced amplitude in the oscillation, but we also see some low order, a greater low order oscillation. Anyhow, also in the first simulation, you can see that there are other frequencies inside. This is mainly due to, if we analyze all the frequency spectrum, this is due to the interference with other modes of vibration. If we enable damping, things goes much better, and you can see the nonlinear oscillation goes very soon into steady state with a good anyhow oscillation around 15 micrometer. After this, we moved to the full system simulation. So we have in this case also the rotor and the we modeled the contact between rotor and stator. We put the rotor, as I said before, at 5 micron distance from the stator. So here you can see the oscillation from 0 are a little bit shifted on the bottom. Also, the elliptical trajectory is shifted in respect to 0, is shifted on the bottom. Here you can see the total normal contact force that multiplied by the constant that we used for the simulation give us the torque in possible torque in the range of micronewton meter. But we will see this more in detail now. If we run a temporal simulation after 400 microseconds, the angular speed, the angular velocity of the rotor is around 13,000 RPM in almost steady state. If we compute the torque, mechanical torque of the system by derivating the angular velocity, if we average a little bit in order to reduce the noise, we get a torque, a maximum torque of around 4 micronewton meter. Also, the peak mechanical torque can be computed in the same way and is around 4 millivolt. The friction in the first case was static. If we enable also dynamic friction in the contact, we see that other modes, vibrating modes, are more present and interfere more with the system. So we have a little bit reduced torque around 3 micronewton meter. The same is for the maximum power, and the speed goes down after a peak of 12,000 RPM around 9. In this simulation, we enable also damping in the simulation. So after a reduced peak of around 9,000, we have a more intensive contribution of the other vibrating mode. So the steady state angular velocity goes down to 5,000 RPM. This work is dated back in 2019. If we tried to compare also the motor with similar diameter motor at the time, and we saw that both on the angular speed and torque, the results were promising. I want to highlight that during prototyping, you can encounter some microfabrication and assembly issue that must be faced. So this work has been only based on simulation. This work has been carried out during a Politecnico di Milano master student internship within STMicroelectronics. So beside the two organizations, so Politecnico di Milano and STMicroelectronics, I want to thank Giorgio Casiraghi, the student in 2019 that carried out most of the work. I am Daniele Caltabiano. I'm leading a small research team in ST Agrate, with working mostly on advanced sensor and smart controls. So I want to say hello to my team in Agrate and Lecce. I want also to thank Andrea Picco from ST for his great contribution on the ST processes, and the Professor Stefano Mariani for his theoretical great contribution.
Okay, thank you very much, Daniele. It's a very comprehensive presentation, and let me tell you something. I was dreaming to have these small motors of 2-3 millimeters in size, being capable to move something, you know. I've foreseen applications like in the cellular phone, you know, the vibrations or whatever. So there are so many things that could be done with that, just, you know, to be able to push it beyond modeling. And, you know, how do you foresee the fabrication as a batch process, I assume, right?
Okay, so your question is about microfabrication. So for the stator, or
the entire process, it has to be somehow integrated, because you have to produce this in one single shot. Otherwise, the benefit of micro machining is completely lost if you have to assemble piece by piece every single thing, right?
Yes, this is a great point. So in microfabrication, the important thing is to fabricate several devices at the same time. So our idea was to build up the piezoelectric stack and the metallization at wafer level. So the full wafer is processed in parallel, holding hundreds of devices. And with the first deep etching, we are starting the singulation of each circular die. And we complete the singulation after bonding the first wafer to a secondary temporary wafer. So in this case, by exploiting, for example, the contact pad or some tape, if we want to have a simple temporary bonding. And this allows us to complete the step first with the deep etching, but second with lapping etching. We could separate all the stator in once. So after this point, we have all the stator which are separated. So either we use a pick and place to put each device into the final package, or if the soldering has been done to a substrate, which is the final assembly substrate, you can complete directly in parallel this microfabrication with the final packaging step, and after this step you can do saw dicing to separate the motors after final assembly. So this is then a trade-off between complexity in all the steps and parallelization of the assembly.
Okay, thank you very much. I'm asking you this question because years ago, Dr. Epstein in MIT, he initiated some work on some micro turbines, and everything was fine till the fabrication, till the realization, which is definitely a very tough point. I'm not contesting that, but thank you very much for the answer. So if it's any other question, I checked the chat. I don't see any.
There's a question in the Q&A box, and they say batch fabrication would probably have some challenges. What are the challenges once going into the production?
It's more or less the same question I had. So it's formulated differently, but indeed that is the concern. Yeah, that is the tough, no doubt, that is the tough issue in here, but we have to start somewhere. I mean, without starting, we don't get in, we don't move. So I fully agree that it's the time to do it, and one day somebody will find a solution to do it, probably to do both, this type of motors and turbines. And
yes, main challenges, as I said before, are this step of dicing, so separating all the stators, so moving from the parallel processing to single stator process. But if you do here in a clever way with temporary bonding, so with a temporary wafer bonding, for example, with some tape, then you can move to package with a automatic pick and place in order to complete the microfabrication with the packaging.
I have no doubt one day we'll find a solution. Not us, or maybe us, but you or somebody else. There will be a solution to the problem. There is a solution to anything.
I can see another question. So for the micromotor, do you expect the challenges of axial pressure? Yes. So we assumed in the simulation a vertical fixed displacement of around 5 micrometer. Axial pressure could be an issue. Another big issue could be friction between all the elements. So this can reduce much the torque, the available torque of the motor, which is already very limited because the motor is really tiny, 2 millimeters. So we are talking about micronewton meters. Another problem could be axial pressure. For sure, one solution could be to decouple somehow the rotor from the actuated device, for example, with some elastic joint.
Right. Yeah, elasticity might be, of course, a way to do it. Okay, so this being said, I want to thank you very much, Daniele, and wish you good luck with the endeavor. I'm sure
thank you, everybody.
Thank you. Enough on your hand right now. Okay, thank you again. And finally, first Belgian presentation from Laurent Francis, my old friend.
Thank you, Professor Stiharu, for the chairing of this session, and also all colleagues at MDPI for the organization of this first-time conference. It's a pleasure to be here with you to present our work on stable porous silicon membranes for fast bacterial detection. I'm Laurent Francis. I'm professor at the Electrical Engineering Department in UC Louvain in Belgium. The work has been performed with Rosalind Verkoteren. She is performing her PhD in my group. And we are collaborating with Jacques Maillon and Audrey Leprince, who are working at the Earth and Life Institute, and they provide us with all the biology and biochemistry we need for this research. Okay, so recently our attention has been concentrated a lot on viruses and their disastrous impact on our lives. But in the meantime, we may have forgotten about another danger lurking in the dark, that are the harmful bacteria. Their danger comes from their increasingly antibiotics resistance, which also has terrible consequence for other living beings. Currently, bacteria and nosocomial infections cause thousands of deaths worldwide and will, according to experts, kill more people than cancer by 2050. One way to strive against antibiotic resistance is to develop fast diagnostic tools. This will enable a quick and targeted treatment and reduce the use of broad-spectrum antibiotics. That's why we aim to fabricate a fast, cheap biosensor that does not require a specific training and can be used in point-of-care applications. Antibiotic microbial resistance is thus a strong motivation for our research, and we address it indirectly through the development of a specific biosensor, to name it here a porous silicon optical biosensor. In a biosensor, we have the combination of two key components, a biorecognition element and a transducer. For our biosensor, we decided to use selective endolysins as biological element. Endolysins are proteins encoded by bacteriophage that can digest the cell wall of specific strains. They can be added to a sample volume and therefore eliminate the need for functionalization, which reduce the fabrication time, cost, and the requirement on storage and usage conditions. For transduction, we use a porous silicon membrane. They are characterized by a large surface area and are therefore very sensitive to minute changes in the environment. Porous silicon has unique optical properties, which is why we went for the optical detection method, since it is also very easy to set up. Now, let me tell you a bit about endolysins. They are encoded and used by bacteriophage at the end of the replication cycle. Endolysins degrade the peptidoglycan or murein of the targeted bacteria, which is the cell wall component. And thus they create an opening in the cell wall for the phage. When there are multiple holes inside the cell wall, this will destroy the bacteria and release its content in the environment. For our study, we used a selective endolysin called PLIV221 encoded by deep blue, which is a phage-targeted Bacillus cereus group. Here you have an example of this targeted bacteria, which is typically found in food poisoning. It's not a very lethal one. You will not die from this one, but it can cause a lot of trouble. On the image here, you see the Bacillus before its lysis. So it's a complete bacteria. And after it has been incubated and the lysis, you can see how its content has been degraded. This will release the cell content all around the place, and we can see some of the debris here around, but you get it all over the place. Now let us look at the working principle of our detection, which is quite simple and straightforward. There is first a pretreatment of the sample where endolysin is added to a bacterial suspension. The solution is then incubated for half an hour at 30 degrees to promote the lysis. And the bacterial lysate is then pushed through our porous silicon membrane, which is under continuous optical monitoring. Non-lysed bacteria are thus filtered out and won't much interact with the probing light beam, which is going indeed to interact with the volume here of the porous silicon membrane. The transducer is optically monitored. Here is an example of the optical spectra before and after 15 minutes of the bacterial lysate filtration. The targeted bacteria was thus the Bacillus cereus with an initial concentration of 10 to the power 6 units of colony forming units per mil. After 15 minutes, there is a change in the optical spectrum that we can see. And when we apply a Fourier transform, we can see that there is a very small change in the so-called effective optical thickness, which is this 2NL factor, where N is the refractive index of the whole compound of the membrane here, and L is the length traveled by the light through the membrane and back. Now let us detail the full fabrication process. Porous silicon anodization is compatible with standard microfabrication techniques. In order to define the porous area, a silicon nitride mask is deposited on a highly doped p-type silicon wafer. Then we use photolithography and reactive ion etching to create a pattern of the area where we want to have the porous silicon itself. Then we have an anodization to create the porous silicon, which is then pacified using thermal oxidation. And then to open the porous layer, a thick resist mask is coated and patterned using photolithography again, serving as mask during the deep reactive ion etching of the back of the wafer. This will automatically stop on the passivated porous silicon. Once we reach this porous layer from the back, the pores are fully open and we have thus a silicon membrane as illustrated here in the picture, seen from the back. A quick word about the fabrication of porous silicon itself. By electrochemically etching a monocrystalline silicon, we have the so-called porous silicon anodization. The principle is very simple. We place a silicon wafer, preferably p-doped, in an etching cell containing an electrolyte based on hydrogen fluoride. Then we pass a current through the cell which induces the chemical reaction, creating the pore as described here. As you can see, the reaction is based on the hole conduction through the silicon bulk. Pore size, thickness, and porosity depends on 3 factors: the HF content, the current density, and the etching time. Example of resulting structure are imaged below, with pore size varying in 2 layers with 2 different porosities, as seen in the cross-section here. This is important because our membrane is composed, in fact, of 3 different layers, which are obtained by changing the current density. We have first a sensing layer, which is only a few microns thick. Then we have a contrast layer, which is there to enhance the optical signal. And finally, we have a mechanical support, which is there to enhance the robustness of the membrane and to avoid it cracks or breaks too easily when exposed to the sample. The porosity is different, and this is very important. The porosity of the sensing layer is very important and quite huge. The contrast layer and the support layer have different porosity, only to allow the flow through of the liquid. If we take a close look at the membrane, we see that it's less than 100 micron thick. This is a cross-section view. And we can also zoom in the sensing layer, where we see the interface with the contrast layer here. What are the performance of the porosilicon sensor? For most porosilicon-based sensors found in literature, there is a flow-over operation where the analyte is simply flown over the porous layer, which is what we see here. In that case, pure analyte is captured in the porous layer, and with our detection protocol, no bacterial lysate can be detected. That's what we see in the graph here. Indeed, the effective optical thickness shift measured during the bacterial lysate detection, in red in the graph, is comparable to the ones measured during both negative control in buffer and with only endolysin in order to make the check. For our device, we use the flow-through approach with our porosilicon membranes. This enables the capture of a lot more of analytes. And for an initial concentration of 10 to the power 6 units per mil of our bacteria, an increase of more than 2% in the relative effective optical thickness was measured after 1 hour. Knowing that 1 hour of detection corresponds to the filtering of 1 milliliter of our bacterial lysate. Now let's take a closer look at the graph. In gray, we have the negative control with only the buffer solution. This induces a slow decrease of the relative effective optical thickness, which can be explained by the slow dissolution of the silicon oxide in the saline aqueous medium. The negative control using only endolysin, which is in blue here, can pass through the membrane and induces a slight increase of the relative effective optical thickness, indicating the passing through the layer, but nothing special can be observed in this case. This increase is, however, within the noise level, which is seen here, and which is calculated as 3 times sigma, the signal of the PBS solution. Finally, in red, when using the bacterial lysate as an analyte, the effective optical thickness increases quickly, reaching the noise level after a few minutes, and the average total increases is after 1 hour was calculated up to 2.35%. As mentioned before, 1 milliliter of bacterial lysate was used for this detection, indicating that we can detect the lysate for this huge concentration, 10 to the power 6 units per milliliter in less than 10 minutes. We can be interested in the limit of detection and the selectivity of the approach. On the left graph, we can see for the same bacteria, the different concentration which are relevant. So we have a detection for sure at 10 to the 5th units per mil, and we may have some signal already detected at 10 to the 4th, but we are in the error range in that case. Thus, the limit of detection is clearly in this range of 10 to the power 5 for the moment, which is still pretty high if we want to make it a practical application. And we therefore need to increase the sensitivity and reduce the noise level in order to have a lower limit of detection. On the right, we'll illustrate another feature of the biosensor, the selectivity. Here we did several tests with also another bacteria, the Staphylococcus epidermidis. And when we have a mix of both, we can see clearly that we do not detect the Staphylococcus, which is not lysate. And we have a clear detection in the case of the mixed bacteria solution, where we have, of course, the detection of the Bacilla cereus. Beside that, a nice feature of the sensor is the versatility. If we change the lytic agent we use, we can detect another strain of bacteria, which is the case here. So we use lysostaphine, which is the one detecting thus, in this case, the Staphylococcus epidermidis. And we see that we have a reaction for about half an hour because the dimension probably of the lysate content is probably not the same size and the same effect than in the case we had in the Bacillus cereus. Still, we have nice detection within half an hour time. I come back to the slide here. We see different effects. The first thing is that we have an error range which is fairly large. Thus, we need to have about 1% of change in order to be sure to be out of the signal error. And the second point, not seen in the graph here, we have shift over the time because the saline solution is etching slowly or silicon oxide material, and thus will have a shift over time. And the shift is, of course, a problem because it will induce false detection. So we were wondering if we could not make it better, and therefore we have added by atomic layer deposition a thin layer of aluminum oxide in the pore, here about 6 nanometers thick, which is going to reduce the dimension of the pore. But we can see clearly that we have a stronger signal from an optical point of view, which is also seen here in the Fourier transform of our signal. When we have this ALD layer, we have a 5 to 6 times higher signal back from the biosensor substrate. But what about the sensitivity? In that case, we can see that the sensitivity is lower, in fact, and which is still to be understood in detail. We have a signal intensity which is higher by about 5 to 6 times, which will also decrease the noise level. But the sensitivity is about twice lower in this case. So finally, the limit of detection should theoretically be lower with the ALD coating on the porous silicon material. There is another advantage from this coating. Here we have comparison of different coatings by ALD on top of this porous material. And in the first case, when we use the freshly anodized silicon substrate, we have this blue curve showing how the signal is shifting due to the dissolution in the saline solution. Then when we have an oxidation, simply we have the green curve, which is here. So we can stand for longer in the saline solution, but the noise is higher, as you can see. Then when we have the aluminum coating, we have the red curve. And then in that case, we see that we have a stable membrane over time and a better resolution due to the lower noise. And finally, we can also, by atomic layer deposition, coat different materials, such as in the blue marine curve here, have hafnium oxide, in which case we have a very, very stable signal and the same noise level than in the case of the alumina. For future work and for the perspective, we have the possibility to enhance further the signal, for instance, by nanoparticle decoration of the porous silicon material, for instance, by gold. It has been reported in literature for other application, or also with silver nanoparticle, where we have preliminary result here showing a slight increase of the signal. And we can also try to push further the material inside the pore and keep them in place, for instance, by using dielectrophoresis in order to assist the particle flow through the membrane. As you can expect, the flow through the membrane is limited by the pore size and cannot be as high as expected. And one idea is to make a flow through in one direction and then back and forth in order to kind of trap the material inside the porous material and thus to enhance the limit of detection, to reduce the limit of detection. As a conclusion, bacterial lysis is a selective, efficient, and versatile preparation of the analyte prior to its actual exposure to the sensor. The flow through in a porous silicon membrane offers an emerging label-free optical biosensing with low detection time below 30 minutes compared to single-ended porous silicon. And finally, atomic layer deposition of metal oxides in the porous material improves its stability over time in saline solutions and may decrease further the limit of detection thanks to a strong signal enhancement. I would like to thank for financial support the FNRS, Belgian Fund for Scientific Research, the large team who contributed to the investigation on porous material at UCL, in particular Gilles Chen, Luma Cugno, and Jonathan Rasson, and for now Clara White, who is doing a master thesis on the mechanical stability and chemical stability of the membrane. I would also like to thank you a lot for your attendance, and I'm ready to take questions. Thank you very much.
Thank you very much, Laurent. So the floor open for questions. So I in this case, I will just break the ice. Hopefully will be more such questions. While listening to you, Laurent, I was thinking, you know, we struggle so much to build compact materials, you know, homogeneous silicon rods and cut from them wafers. And then your idea is that you have to make them fragile and porous, which is sure it's a paradigm here. It's very interesting to from the philosophical point of view. That makes a lot of sense because apparently not the perfect order makes sense from the life sustaining point of view, but the other way around. So what I have in here, I had this ability of creating of this porous silicon. It's not only one way. You might have multiple ways to build up this porosity within the material. Is any plan to do an investigation on the extent of where the porosity technology or the method of creating porosity in silicon will lead from the sensitivity point of view? This is one aspect, and you try to relate to bacteria. Again, the same thing might be extended to viruses, no? You never know.
Totally. Maybe on the first comment, I fully agree with you. I think as engineer or scientists, usually we try to see a lot of order, but in fact, from disorder, we can gain a lot. In nature, optical structure, for instance, are coming up from some disordered nanostructures, and they work perfectly, and they are making a perfect optical signal, for instance, in butterfly, something that we analyzed in the past too. So we should not be always looking for strong order in all material that we are creating. Even our first presentation today presented nice optical effect when we have something which is relatively dispersed, in fact. So we have still a lot of work to perform and to be more flexible, to be more in relation with what we found in the biological world, which is usually very fuzzy, very chaotic, in fact. And from there comes some very nice features. Now, speaking about the porosification, clearly porous silicon is not the only porous material which can be used also. There is aluminum oxide, which has been obtained by such a, well, not porosification effect, but they can be porous as well. They can have also some optical properties. They are very fragile, by the way. So mostly when we have membrane, we need to tackle the issue of the fragility. And in some cases, the fragility can be a benefit, in fact, when we want to make it breakable or to be a single use, for instance, we can take benefit of that. So no, indeed, there are different techniques to make porous silicon. Here we use this anodization. There is also another technique called MACE, where we use, in fact, metal-assisted chemical etching to get this porosity. What is very interesting with the approach we have in the case of anodization is what has been shown. You can change the porosity during the process itself. So you can select the type of porous material in the stack during its fabrication and change it on the spot. And this allows us to have, for instance, very large porosity, which can, for instance, be able to trap the bacteria. And then once we have them trapped, to be able to dissolve them and to get their material through smaller pores. The final vision is to have a fully embedded microfluidic system, including, of course, all the fluidics embedded with this porous silicon material. We have still a long way to go, of course, but that's clearly where we can go because of the technological possibility. So yeah, clearly we still having a lot of possibilities there. And the nice feature for the future will be this inclusion of nanoparticles, which allow us to probably enhance both the optical signal, but also the interaction with the species that we get from the bacteria themselves. For the moment, we are just splitting the bacteria and take all its content. But later we can imagine to be more precise and to be focusing on specific material included there. And why not maybe to go to viruses? As long as we have some interaction, we clearly can change the refractive properties of the membrane and thus get some information. The real challenge here is to have a very, very low limit of detection. Again, and I want to stress it out, the concentration that is shown for the moment is very large. If someone has that in his blood, for instance, he's already dead for a long time. At usual septicemia cases, we are in the range of 10 to 100 bacteria cells per milliliter of blood. So here we are a range of 3 or 4 orders of magnitude higher before we have a fair detection. So we really need also to use the techniques that we know from, and we will borrow from microfluidics in order to enhance the concentration, to be able to avoid to have to reproduce too much on the wafer or on the microfluidic system or the bacteria before we test them. And clearly, finally, we have to go to samples which contains a lot of different material. If we take a blood sample, it's crazy the amount of other kind of particles that we find there and that we need to, of course, avoid as a perturbation into a measurement. So a lot of work, and clearly, and this is a call for everybody. If you have idea and want to collaborate, be welcome, because we will still be facing a huge issue with this bacteria in the future, for sure. They are becoming clearly more and more resistant against antibiotics. And there is a call of what we name the superbug, which will be perhaps one bacteria that will fail to be killed by any antibiotic. And once this can become a reality, and I believe we get through quite close to that, then we may face the same issue that we have been meeting here with the COVID, something that gets out of control very quickly, and that can spread by many, many different ways. Some bacteria are spreading just by the air as well, like COVID. So we have the same enemy in front of us.
Okay, thank you very much for the comprehensive answer. And I really, this is like a nice philosophical chat in science, right? Which yes. I miss very much since I'm not going regularly to work. I wish to thank you very much, Dr. Laurent, so Francis, and to greet Dr. Madou. Good morning. I know that for you it's very early, Dr. Madou.
Yes, thank you, but it's okay. I'm actually on a short vacation with my grandkids here in Joshua National Monument. So if they come in screaming, I'm sorry.
It's okay. It makes sense. It was supposed to meet you twice in Mexico, one in Querétaro, once in Instituto Politécnico Nacional. But
there we go.
Never happened. So there we are. It's first time we meet. And
nice to meet
I
you.
use your books, by the way.
Oh, thank you. Thank you.
Okay.
So my talk this morning is about a very recent development in my team, where we are using the technique of origami, which, as you know, involves originally folding of paper in interesting shapes like this crane bird here. But what we interested after making one of these folded shapes to convert it to carbon. So the paper bird here on the right was put in a furnace at high temperature and in the absence of oxygen. And if you do everything right, you can make this paper origami into carbon origami. Actually, the picture specifically is from one of my former students, Rodrigo Martinez, who's now at Clemson University. So that will be the topic I will be talking about. But obviously, I don't want to do this folding by hand. And I'm going to show you the progress we've made to self-assemble from polymer precursors all kind of 3D shapes. We also will talk a little bit about the microstructure inside the carbon material you're ending up with. So first of all, a teeny little bit of history on origami folding by hand and how that can be converted to carbon structures, carbon MEMS. So for example, this one, right? We went from paper precursor material to carbon. Then in around 2007, some interesting work from a group from France illustrated this use of elastocapillary to fold PDMS sheets. And we really thought that to be very interesting and were surprised that that didn't go really anywhere. There wasn't much follow-on. And so I guess now about 3-4 years ago, we came up with this idea of using the same forces, elastocapillary, which is basically in this case putting droplets of water on a sheet, and then the surface tension will assemble the shape. But we were not using PDMS, we were using photoresists that dramatically increased the possibilities here. There's many more shapes accessible this way. But still, we didn't like the idea that I needed to use droplets or elastocapillary. And then more recently, we've been able to do complete self-folding by building in strain into these polymer sheets we are making. Few words about application and then conclusions and prospects. So I will be short here, right, because I don't want to go into all of this detail of where origami came from. We all know paper was invented in China. Then origami became very popular in Japan. It was first more ceremonial, and it came to be regarded as a new form as art. That's in the 17th, starting early 17th century. And it basically became a more popular art form once one was able to mass produce paper. Europe also had a tradition of paper folding dating back to the 12th century or even before, when the Moors brought a tradition of mathematically based folding to Spain. Just to see how far this can go in terms of art form, this is Le Manteau de Montezuma by Correra. Really a very nice illustration of what kind of shapes can be made. But of course, we are more interested these days in mathematically predicting what we can basically embed in a material. And an interesting documentary, you might want to check out this, it's called Between the Folds. I've put the link over here. And that is in a way what we will do here today. It's basically mathematical origami where we use modeling to predict what shape we will make at the end of this new origami process I will be talking about. Here you see a first example, kind of referring again to Rodrigo Martinez, who was making shapes like you can see here, some complex paper folding exercise was followed by pyrolysis. And again, pyrolysis, just like paper folding, is a very old art. Perhaps, pyrolysis might be one of the first things mankind developed as a technology. In this case here, you're actually looking at the kiln where wood is being put into a heap of earth and then heated, which is basically what pyrolysis and carbon MEMS is all about. You have a precursor, in this case paper, in this case wood, and you put it at high temperature in the absence of oxygen, and out comes a shape in carbon that's the same shape as the precursor, except it's shrunken a lot. Some people have pushed this quite far and literally. This example here is actually by Bidan Pramanik, who at that time was a postdoc of mine in Mexico. And having left his wife in India, she sent him some hair, human hair. And after pyrolysis, he found out you make these cute hollow carbon fibers. And actually, he was using it for some electrochemical experiments. Anyways, that's historical background connecting pyrolysis and paper origami. So now we come to a first step in the evolution towards what we're going to be presenting today. And that is to do the folding of the paper, not by hand, but by elastocapillary. And as I told you earlier, this was work first presented by Pai et al. In 2007. And the idea there is then indeed, let's say here, you have a flower cut out with scissors out of PDMS, or here you have a T-shaped structure. If you now put a droplet of water onto this shape, it will self-assemble. The forces involved are elastocapillary, which is a two-way interaction between the liquid and the structure, driven by surface tension of the liquid to minimize surface and elastic energy. In a way, you can see this phenomenon when you come out of the bathtub, where your water strings together with the water droplets and takes on shapes surrounding the water droplets. It's also the way a hummingbird takes honey out of this vessel here. The tongue is split, opens up around the honey, and then is pulled back, as you can see here. So that is the forces that this group was using, Pai et al., to make these PDMS structures. But there's quite a few shortcomings on this approach. What are these shortcomings and what could be done next? Well, number one, it's difficult to pattern PDMS, right? I mean, you can make these shapes, but this is not a photoresist. So you stay in quite large devices to do this. Secondly, it's difficult to distinguish between the folds and the faces. So these are faces, and the fold here, you would like that to actually have another material property than PDMS in the faces. In the Pai et al. Approach, that's not there. There's really little difference, actually none, between this fold area and the faces. Number three, you're not able of making permanently folded structures. Yeah, indeed, when the droplet is gone, the structure falls back apart. It's also not possible to fabricate folded structures on a surface. Say you want to have this flower anchored or this cube anchored with this face. With PDMS, that's not easily done. 5, it's impossible to fabricate rigid structures such as carbon. And so these 5 items were driving us to look at alternatives to make self-assembling structures. And so here is a slide I will spend quite some time on because this is kind of the secret sauce. It shows you how we can, by using elastocapillary of patterned photoresist, make pretty much any shape we so desire. So first of all, what do? We have a wafer of silicon. It can actually be any flat substrate. We coat that wafer with SU8, a photoresist. We do soft bake and first exposure. And what we make here, as you can see, is the same shapes Pai et al. Was making, namely a pyramid, this one, and then this cross structure. Now, you can see that after a first exposure, I'm doing a second exposure, and that is key. You see, because in the second exposure, I can send more UV photons onto the planes, the faces, strengthening them and leaving the folds over here with one exposure only. The consequence of that is the faces are stiffer and the folds are more flexible. So after developing and cleaning, I end up with these shapes that actually have much better distinguishing features than a plain PDMS sheet. Because indeed, I have folds with a lower Young's modulus, so it can flex, it can flap, and I have faces that are stiffer and will not fold as easily as the folding hinges here. So you can see that after I've made my precursor sheets, and mind you, I'm not doing this once, right? It's lithography. I make thousands of those all at the same time. Then, just like Pai et al., since we're going to use, in this case, still elastocapillary, I'm putting droplets onto the shape, and voila, I have them self-assemble around this droplet. I will show you a movie about this process shortly. I now let the droplet inside evaporate. I expose it a bit more, and I end up with nice polymer precursor shapes. I can make any platonic solid. I can build you a house if I build windows in these structures, etc. And at different length scales. So in a way, we see this almost as a new paradigm in manufacturing, because look, when this shape is assembling, I can, with a video following its assembly, and I can stop it at any moment. That means it's really free-form manufacturing. So what do we think we got here at this point? Well, we expanded the photoresist application domain. We have now hinges and faces that are distinct. With the first remark, what do I mean here? Well, I mean, photoresist so far has typically been used in 2D, in 2 dimensions. What I'm doing here is truly make 3D shapes. The hinges and faces are now very distinct. I can easily make anchored and free 3D photoresist shapes. You know, to leave it anchored, I just make it such that the material underneath forms a good adhesion and has a sacrificial layer underneath those faces that I want to lift out of the surface. The faces can be further patterned. Like I said, I could build a house. I could put windows in here, doors, etc. The faces can be further patterned indeed. And then, as I already indicated, I can do free-form manufacturing because I can freeze these shapes as they assemble at any moment by just sending more photons in it, cross-linking the polymer further to strengthen the shape that I see at a given moment. And then, of course, this being carbon MEMS, all these shapes I can eventually convert to carbon. So let's show that. This is the shape, in this case going to a cube. And this is the same shape after pyrolysis. And these are the shapes in carbon. You can build pretty much any platonic solid you want. Over here, you again see the polymer shape and then the shrunken carbon shape. If you look into the carbon material here, the microstructure in this case is very glassy-like, as you can see from the Raman spectrum, with prominent D and G peaks about equal in strength, indicating a glassy carbon microstructure in here. And by the way, this is a typical furnace we use to convert these polymer shapes into carbon. This is a furnace that we either completely fill with nitrogen or another inert gas, flowing inert gas during the pyrolysis cycle. By the way, the temperature cycling is extremely important. How fast you heat, how long you stay at each point when gases escape the polymer precursor, and etc. It is somewhat of an art form. So let me show you two videos. Here, the droplet is sitting on a polymer sheet. And here we go. You can see the polymer faces self-assembling around the polymer droplet. You can see we chose the droplet a little bit too large here, and it couldn't completely capture the droplet. Over here, we have the droplet by heating coming out of the cube. You can see the droplet escaping here. One of the faces lifts off and droplet can come out of it. So I'm gonna just hold here for a second and ask if anyone has a question so far. So what we did is first explaining what carbon pyrolysis is, a precursor to carbon. Then we were talking about hand folding and pyrolyzing that. Then we were looking at Pyadal that in 2007 folded PDMS with these droplets, and how by going from PDMS to a photoresist, we have much more opportunities to push this further. Any questions on this before we set the next step? The next step will be not to have to use any droplet at all. And basically using programmable, self-foldable films as origami-based manufacturing. So we want to get rid of the droplet, and what we really want to achieve ultimately, this technique to be scalable in numbers and sizes, make any complex shape, it being self-folding, should be simple construction, free form, and minimal materials consumption. You can see here some of the modeling that our team has been doing. Actually, no, this one is not ours. That's one from the internet. Sorry for that. But here you see how you assemble something into a rabbit. But these are our shapes. For example, this was the target shape. We then program our material to have regions of more stiffness and lesser stiffness, and end up with a polymer structure that we wanted to begin with. So what we do is basically naively, let's say I have one polymer sheet that you can see here, and I have a fold that has a certain length and a certain stiffness, right? That's a single photopolymer film as the precursor. We then organize the width of those into a structure, like in this case, you can see this toroid that we wanted to make. You can see how you unfold it first, and then how by heating, because we have strain built into the film, you end up with the shape you wanted. So really an end-to-end free-form manufacturing method. So to go from this polymer origami to carbon origami, we needed to get rid of what induces this folding differently from a droplet, as we saw in the previous work. Well, the way this was done is really by thinking deeply about what happens when you develop a photoresist. Look, in this case, like before, I have faces that are more cross-linked and folds that are less cross-linked. That means this here is stiffer than this fold. And if I have this locked onto a surface, I basically have a bilayer. And when I do heating of this film and cross-linking, I make this nice bend in the structure. and the bend will depend on the escaping solvent in the fold region. So here, differently from using the droplet, we are using the forces that occur when by heating, you have the solvent evaporating out of the polymer material. When you see this symbol here, it means cross-linked polymer chains. And then when you have these non-cross-linked polymers, we indicated by chains like you can see here. This means the developer over here, and then this is the supporting structure. So by manipulating those, you can actually make many more films that you desire. So here, I'm repeating now the process, which is a little bit different from the previous one, where we were using droplets as actuators, so to speak. So we use PDMS now not as the active material, but as the support. And on it, we spin over SU8, and all of that is on a silicon wafer, right? And now we have a film that's really not attached to the PDMS at all. It can very easily come loose, but the solvent cannot go down, it can only go up. And by the way, that is still an issue that we've recently also have tackled. In this approach, you can imagine, because there's a substrate here, solvent cannot go this way. So that means we only will have folding upwards. We don't have folding downwards. Although this, we are currently also publishing, we found a way to have folds going this way and folds going the opposite direction. But in any event, at this stage, all we could do is have the films bent upwards by solvent evaporating upwards. So here you see a specific shape we wanted to make. Like before, we have a first UV light exposure, cross-linking to a certain extent. Now we do a second UV exposure. And you remember what the second UV exposure does is make those areas you want to be stiffer, they make it stiffer. And the areas that have been exposed only once will constitute folds. And so after the post-exposure bake, developing and removing from the PDMS, we have these freestanding pattern thin films that now we heat, and voila, by folding, by heating, we create all of these structures. Pretty much anything you can dream up, we can make. And then again, we can go from these polymer shapes to carbon shapes. So that's fabrication and summary. Silicon wafer, PDMS spin coating and curing. This is the silicon wafer with that PDMS. Now SU8 on top of the PDMS. First exposure to cross-link these areas somewhat. Cross-linking in a second exposure a bit further, so you distinguish faces and folds, and then taking these shapes off. You have now these freestanding shapes, and it doesn't need to be one, it can be hundreds, it can be thousands of those sizes you can control with lithography. Self-folding simply by heating, and then here is our folded film. And if you want to make it stiffer yet, you give it another exposure and you have your plastic polymer structure. And then if you want it so, you could carbonize this. I will not spend a lot of time on the modeling. That would take me easily another 20-25 minutes. But as I kind of indicated, what are the variables we have to control this whole folding exercise? Well, we have the width of the fold area, we have the thickness of the film, and we have this length B here. And then this theta here is this folding angle. And that is basically what you put in your model. And without going into the detail, we have the diffusion equation controlling the solvent, evaporating the concentration gradient of the solvent in the film, that causes really your actuation strain field. And it's that strain field that causes the bending angle theta. You can see here, this is fold width over fold thickness, and millimeter over a millimeter, and that's the fold angle. And you can see these are experimental points. You can see the fold angle, and our experimental result for the fold angle follow nicely the expected slope based on our little model. So that's the modeling fold angle programming exercise. I will skip this. It just goes into more detail of how to control this self-folding. And again, I will give you these slides so you can study this. And also this is being published. This shows the complexity of the shapes we can make. And again, you can see no droplet here in the assembling of these cubes. Here you see the meshes that lead to the desired shape. There we go. Just to show that you can really push this very far. Here we're making a little table. And here we're making a trim torus. So I do believe that this is pushing freeform manufacturing quite a bit into a new direction. And since this can be carbonized and then perhaps metallized afterwards, I do feel that this broadens the field quite a bit. And some of you might know, it's been my push for about 10, 15 years to see carbon not only as our preferred material in terms of all these allotropes, but also as a material that can easily generate the same shapes and more interesting ones than silicon can. More shapes. And so for applications, well, at this moment, we're actually enjoying ourselves mostly, but you know, we're thinking about micro grippers, 3D electronics, encapsulation, flipping micro mirrors, scaffolds, etc. So conclusions, we achieved solvent transport-based self-folding using single-layer photopolymer films. We developed an end-to-end freeform manufacturing method by leveraging the unfolding polyhedra method. We demonstrated the method with different shapes, converted polymer shapes to carbon, and developed a new bidirectional folding strategy. You can see this is in a different color. I didn't detail that yet. And so that is coming perhaps for the next talk. With that, I'd like to thank you. And maybe some of you remember this monolith in a very famous movie by Stanley Kubrick. And perhaps we can imagine what they really found that monolith to be was carbon. So with that, I'd like to thank you, and hopefully we can entertain some questions.
Thank you very much, Dr. Madou. Very nice talk, and lots of questions still there, so which is good. It's food for thought, right?
Yes.
This, I mean, what you do, it's definitely a natural phenomena that you try to control, because folding, it's a very well and ancient process. All the proteins inside our bodies, the RNA, it's folded, and if in case it doesn't fold correct, you know, this could lead to very serious medical conditions. So trying to find order in that, again, was discussion I had a bit earlier with Laurent. It's our, I would say, push need to put order in nature, but nature is not necessarily organized in a linear way as our thinking is.
Right.
So I think
You know,
I mean it's a long chat about that. Would be interesting to have.
But by the way, you made me think of something that we attempted. We were so eager to see what natural precursors we could convert into carbon. And for 3 or 4 years, I gave my students the goal, and maybe this is a goal for this group here, to take circular DNA and see if we can pyrolyze it to make the world's smallest ring. Just to see, but because in a way, this pyrolysis process is amazing. If you think about it, you go from paper with all of these other atoms, and when you heat, the nitrogen comes off, oxygen, water, but the carbon reconnects, right? It's one of the few materials that self-polymerizes. And so we thought, would it be possible, perhaps we need to decorate the circular DNA with some carbon-rich material to follow the shape, maybe polythiophene or so. And then you heat it, and of course, you need to find it afterwards. We never succeeded so far. But then if you would do that with proteins, it's probably impossible there because it's too much hydrogen bonds. And these, you know, in our structure, obviously, are covalent bonds that you end up with. But again, perhaps you could decorate the protein 3D shape, and then you pyrolyze, and you end up with this 3D shape. No more X-ray crystallography for protein, which is very difficult. You know, just dreaming here.
Right. Carbon nanotubes, it's more or less the same thing. You know, they've been discovered in a reactor where they were, you know, making electrical discharge, right?
That's right. Yeah.
So they figure out that, you know, something like that, it's a resultant of the high energy and of course existence of carbon gas. Right. If it's any other question, I try to polarize the interest. Please ask it now. It's a unique chance to catch.
Well, I have 2 questions here from Nathan and from John.
Okay, go ahead, please, then.
So for origami, do you think the future includes larger self-assembled structures made from components that have first been self-assembled? Yeah, look, that's kind of a very obvious direction they should take, right? The structures you've seen here are all in the millimeter, 1 millimeter and below. And of course, with lithography, it's hard to go to a centimeter, 2 centimeter, etc. So it's probably limited if you stick with lithography to these dimensions, but you don't need to, right? Because you could use batch illumination of a whole sheet, and then perhaps with a laser make these creases that I'm showing. And if you modulate the stiffness of the hinges versus the faces, you could do the same thing on bigger structures. So I really hope that we get next generation scientists here jumping on this to make that indeed a bigger paradigm that's not just limited to structures below 1 centimeter. There's another question here then from Restrepo. I have a question. Although we can achieve the desired shape, experience with origami shows us that connections that are not rigid can present loss of stability in the face of forces such as compression, as they have thought about how much a piece must be bent to ensure that it fulfills a specific question. Let me think about this a bit. So, yeah, I mean, doesn't this really depend on how good you can distinguish the Young's modulus between the two? Because indeed, look, and actually, if I had gone more into detail in the modeling, you could see that we are compensating for these defaults. Because what you're really worried about is the rounding of the corner, right? And in extreme, you would have a ratio of the Young's moduli that's as high as possible. and then you would end up with a 90-degree angle where you want it. But I think what you meant to convey here is that it will remain somewhat rounded. Is that right, John? Is that really what you're after? Have you thought of any techniques so that when bending, you can allow the ends to interact, making them rigid? But yeah, John, look, you have that capability automatically. As I told you, you can cross-link further. I just send more photons onto the structure.
So Jonas answered yes, thanks.
Oh, okay, very good.
I can't see any more questions.
Okay, thank you all. I'm gonna join the grandkids here. They're getting to leave.
We thank you very much for the meaningful talk, and hopefully we'll see you in person one day, Marc.
Yeah, absolutely. Looking forward. Thank you all. Bye.
Thank you. Thank you. So now we should probably wrap up. I have a class right now in 7 minutes, in 5. So this being said, our session has ended, I believe, successfully. We had all 4 papers presented. Absolutely remarkable papers and the remarkable work, outstanding results. So I would encourage you to continue to attend the conference. Keep in mind the first one. First might not be the best, but you know the second will be definitely the successful one. So I encourage you to attend the second conference that will be definitely organized next year. Now we'll have other sessions that are announced by schedule. And this being said, I would like to thank the participants, the speakers, and I will invite you to continue to attend the rest of the conference. Thank you very much.
Thank you to everyone for your time, for joining us, either for talking or just listening. The next session is next Friday. Registrations are still open, so you can go register. It's on the conference's website. And have a good morning, afternoon, evening, wherever you are. Thank you very much.
Thank you very much, Charlotte. Thank you.
Bye-bye, everyone.
Bye now.